Alright, hello everyone, my name's Logan, welcome back to the lecture hall, and today is a great day because we're finally actually doing calculus. We're finally moving on to chapter 2, limits and derivatives. Today we're going to be going over section 2.1, the tangent and velocity problems. So I've been saying a lot about tangent lines. What does it mean? Well, it comes from the Latin word tangens, which means touching. And a tangent line to a curve is a line that touches the curve one single time. So for a circle, that's pretty easy. You can see it, so let's get a color green. So there's a tangent line here. It just basically kisses the curve. And we got one over here. And we have them all the way around the circle. At every point on the circle, there's a tangent line to it. And for a parabola, they look like this, very similar. It touches the curve at one point. Right? Alright, so, but how do you find the tangent line? Well, the first thing you need to do is find the slope at the point where you want to find the tangent line. So, and that's not too hard. We all know how to find the slope from Algebra 1 after all. But to find tangent line slopes, we need a little bit more, and we got to learn a little bit more, so that's what we're going to do. So, from Algebra 1, we know that the equation of a slope, m is equal to y2 minus y1 over x2 minus y2, or x1. And the tangent line of a graph only touches the function at one point. So we need to do something different. And the easiest way to find the slope is through derivatives. But we aren't quite there yet, so we need to start with an approximation of m. So if we wanted to find the slope of the tangent line to the parabola at y equals x squared at the point 1, 1, we would need to choose a point Q that is very close to point P, and then this will create a secant line with slope MPQ. A secant line is a line that intersects a curve more than once. So a secant line to the curve, to this curve, if it was like here and here, it would look like this. But what we're trying to do is we're trying to find the here and here. See, these points are very close together, so it's almost to a tangent line. So, a secant line won't be tangent, but let's just continue with the approximation. So we can choose x equals 1, because then p equals q. So let's try with the point, or we cannot use x equals 1, because then the point p would equal to q. So we should try with points 1.5. So let me erase this. So we have our x squared minus 1, x minus 1, because this is our y2, that's our y1, this is our x2, and this is our x1. So now we're going to plug in the point 1.5. So we plug it in, and this is equal to 1.5 squared minus 1 over 1.5 minus 1, which is equal to 2.25 minus 1 over 1.5 minus 1, which is equal to 1.25 over 5, which is equal to 2.5. So our secant line slope is 2.5, but let's plug in some more points and slowly get closer and closer to 1. So I'm just going to draw the table real quick. Alright, so we have our two tables, and I say two tables, and you may wonder, oh, I thought you were just going to draw one table. Well, we need to do it from the left side, so approaching 1 from the left side, so you start at 0 and approach 1, and then you have to do it from the right side where you can start at 2 and approach 1. So, as we can see, x is x is 0, MPQ, which is the slope, is 1. 0.5, 1.5, 0.9, 1.9, 0.99, 1.99, 0.999, 1.999. So we can see, all right, that's pretty much getting close to 2. So now let's look at the right side. So x is 2, MPQ 3, 1.5, 2.5, 1.01, 2.1, 1.001, 2.01, 1.0001, 2.001. All right, so we see, well, both sides seem to be approaching 2. So this suggests that the slope of the tangent line is at the point, the slope of the tangent line at point 11 is equal to 2. So we say the slope of the tangent line is the limit of the slopes of the secant lines, and this can be written like so. The lim, this is LIM, as Q approaches P is equal to M PQ, which is just equal to M. And then if we were to write this with numbers, the lim for our x squared as x approaches 1 of x squared minus 1 over x minus 1 is equal to 2. So now that you have your slope of 2, you can plug it into the point slope equation that, as I'm sure you all remember from Algebra 1, y minus y1 is equal to the slope times x minus x1, and you plug in the point, y minus 1 is equal to 2x minus 1, and you distribute and get y is equal to 2x minus 1, and you have your tangent line for the function y equals x squared at point 1, 1. So that was a lot, and you're probably wondering, what's the limit? How does finding the tangent line help me? And I will explain what exactly a limit is in the next video. And now we will look at some applications of tangent lines right now. To understand applications of tangent lines, you must first understand that the slope is the average rate of change of a function. But when you have a tangent line, that is the instantaneous rate of change of the function at the point. So an easy application for this is velocity. So this is where tangent and velocity problem comes in. So for our first application, we're going to be dealing with velocity. So let's say we have an equation for position. S of t is equal to 4.9 t squared. If you've taken kinematics or physics 2, you might realize that this is the equation for an object falling, but that doesn't matter because this isn't physics class. But so if we wanted to find the position of the ball after 5 seconds of falling, how do we do that? Well, we don't know what limits are quite yet, so we approximate. And we'll just do this with 5 and 5.1 seconds. So we have our equation 4.9 times 5 squared, or 5.1 squared, I'm sorry, minus 4.9 times 5 squared all over 5.1 minus 5, and this equals 49.49 meters per second, right? So then what we can do is write out the table yet again, and we can see, okay, x equals 5.1, velocity equals 49.49, x equals 5.05, velocity equals 49.245, x equals 5.01, v equals 49.049, x equals 5.001, velocity equals 49.0049. So, as we can see, it's as x approaches 5, velocity is getting a lot closer to 49. So we can assume velocity is equal to 49 seconds at t equals 5. Alright, that's all for the applications part. There's many more applications that tangent lines can be used, and we're going to go in depth in the near future. And I'm sure you're probably a little confused on limits. Don't worry about it. I'll be making videos. This is just the intro lesson to limits, to kind of get your feet in the water, kind of learn about approximation and that sort of thing. So that's all for the lecture portion. And now we're going to transition into some questions. Alright, so we're just going to be doing number 2. A cardiac monitor is used to measure the heart rate of a patient after surgery. It compiles the number of heartbeats after t minutes. When the data in the table are graphed, the slope of the tangent line represents the heart rate in beats per minute. The monitor estimates this value by calculating the slope of a secant line. Use the data to estimate the patient's heart rate after 42 minutes using the secant line between the points with the given values of t. What are your conclusions? So, we're going to be finding the secants between 36 and 42, between 38 and 42, between 40 and 42, and 42 and 44. So let's do that. So, first one, you get your slope. M is equal to 42 minus 36, right? And then we have 2948 minus 2530, and then, so we'll just plug this into the calculator. 2948 minus 2530 divided by 42 minus 36, and that equals 69.66 repeating. Alright, now between 38 and 42, 2948 minus 2661 over 42 minus 38, not 38 minus 42. So that is 2948 minus 2661 divided by 42 minus 38, and that equals 71.75. Now on to 40 and 42. That's 2948 again minus 2806 over 42 minus 40, which is 2. 2948 minus 2806 divided by 2 is equal to 71. And then 42 and 44, that is 3080 minus 2948 over 44 minus 42. Alright, 3080 minus 2948 divided by 2 is equal to 66. Alright, so what are your conclusions? Well, you can tell their heart rate ranges between 66 and 71.75, which is approximately 72. So you could take the averages of these. So you could do 69.66 plus 66 plus 71 plus 71.75. Divide that by 4, and that equals 69.6025. So you could say the average heartbeat beat per minute is approximately 69.6. So we're only going to be doing one question because I did the velocity question in the lecture portion. So that's all for today. My name was Logan. Thanks for watching. Have a great day.